quick introduction. So Luca Müller is at the University of Bremen. He works on where CHERI meets verification and virtual prototyping. He builds CHERI-enabled RISC-V virtual platforms that enable early software development, security analysis, and hardware experimentation. Right. So over to you.
Thanks for the introduction.
I'll just put this down.
Yeah. Funny how they put the two Germans next to each other, and then they have the same last name as well. So, all right. Everyone warmed up now. So, yeah, as mentioned, I will introduce today our CHERI-enabled RISC-V virtual prototype, which we are building in our group, go into its capabilities, and also some potential applications we are researching. So, this was already mostly done, but the most important part of this slide is at the end. So I want to mention that I'm not the only one doing this work. We are a larger working group, actually some researchers who are looking into this topic, and I wanted to give a quick shout out before I get started on this. So for the agenda, I will briefly talk to you about why we need virtual prototypes, why they are relevant, go into the capabilities of our CHERI-VP platform, talk about 3 applications we're doing research into, and then also looking at future directions. So why do we need virtual prototypes? Why are they relevant? If you're looking especially at embedded systems where you are unsure yet what you want to build in software and what you want to build in hardware, waiting for a full RTL implementation can really delay your software testing and also hinder your software hardware co-design. So virtual prototypes aim to offer this early evaluation while giving you an executable model of your hardware in software actually. Another upside of virtual prototypes is that a variety of platforms can be modeled by this. You can do some exploration of what you want to build in software, what you want to build in hardware. You can really go from these small embedded devices also to larger scale systems, because you just not only have the simulator support like you would have for something like QEMU, but you can also model your complete platform with peripherals and other things. So relating this to CHERI, we want to do might want to do some early evaluations on some CHERI-specific features of our hardware, and this can be done with virtual prototypes in a pretty early stage. So going into the capabilities of our platform, it's built on top of our RISC-V VP, which was published by our group in 2018. It's a RISC-V 32 GC virtual prototype, which is implemented in SystemC TLM-2.0. And our CHERI-VP adds some support for 32-bit pure capability RISC-V binaries to be executed on the platform. So as you would expect also from a classical RTL design, when you want to extend your hardware for CHERI, you have to touch most parts of the architecture. So you look at the instruction set simulator, but also at the memory model as well, TLM bus, and so on. You can build your C or C++ software which you want to run on this platform with a custom bootstrap and linker script. So some parts of the setup are done on the platform on the VP level, and some need to be done by the software as well. So looking at what the challenges were during our design, we had 3 main takeaways, so to say. The first one was that the largest portion, the most time spent in our implementation, went towards adding the new CHERI instruction to the ISS, seeing how they affect your platform, everything they involve. The second was that most debugging, most issues went into handling tag memory correctly, ensuring that tags are correctly propagated and correctly handled in the given CHERI instructions. And on a more positive note, we found that the CHERI technical report, as well as the SAIL reference model, posts as really useful references to really see how things can be implemented, also to find bugs and advance the implementation. So going into the applications I was mentioning, first up, what we are doing is, of course, verifying our CHERI-VP somehow to see if it complies to the ISA with the TestRIG. So we added support for TestRIG that it can communicate over the socket, get the instructions, generate the traces to compare to the golden reference. With those tests, we were able to find some issues, especially related to how tags are encoded. Okay. Can anyone still see? Okay, I will just go on. And and also exception handling was an issue. Okay. So yeah. Oh, perfect. Speaking of issues, okay, so getting back to topic. Yeah, so most of it was on tag encoding and exception handling. We are still in the final stages actually of verifying all the corner cases which pop up. So speaking towards the open source nature of our virtual prototype as well, we expect to have it out soon. With the CHERI support, you can already have the normal RISC-V VP on GitHub. Extending this TestRIG verification work, we also are looking how we can evaluate the effectiveness of TestRIG itself for verification. So to this end, we want to inject a mutated instruction set simulator into our virtual prototype. We do this by our custom built mutation generator, which has some mutation classes defined, which are explicit to CHERI as well. For instance, having some switching up the exceptions which are thrown, and then we want to see and evaluate how effective these mutations can be found with TestRIG, how many instructions you need, how much runtime you need, if they can be found at all. Second application we're looking into is the detection of security vulnerabilities in software. So, as we are all aware, these capability violation faults which occur when you run something on CHERI can help with the detection of security vulnerabilities in existing hardware. We've also heard a bunch about CWEs before, so mapping these weaknesses, these security violations onto your software and see how they can be mitigated by CHERI. So the idea is, if you look at the figure here on the right-hand side, it's really all centered around our VP-based platform simulation, which includes our virtual prototype, the CHERI architecture, and a threat and fault model. In the future, we also aim to add some symbolic executions such that the software can be more thoroughly explored as well. And the goal is, with this platform simulation, you have to go from this unsafe edge and IoT application, which we know nothing about in the end, regarding to security, to the safe and robust application, which was verified. So some early evaluation we were doing so far showed that for the CW examples provided, we can find those pretty easily with our VP. And yeah, next up is looking into larger scale softwares, also the CVE, which map to the CWEs, which are relevant to see if we can detect those pretty effectively. Last application is more pertaining to the CHERI hardware itself. Actually, we're looking into how we can use in-memory computing explicitly for the tag computations. So, of course, one of the overheads introduced by the CHERI architecture is having to deal with tags every time we want to touch a capability. Memory operations are generally slow, so we want to see how we can speed this up. For this, we use the TestRIG again to generate what we call security-aware instruction sequences, which really just means going or guiding the random instruction generation done by the TestRIG to have more realistic scenarios with more memory operations, and see how we can then evaluate on those instruction sequences. Our first evaluation showed that we can achieve speedups between 6 to 11% for under ideal conditions. The span comes from the fact that we assume different runtimes for the in-memory computation itself. Of course, it will not run in 0 time. So yeah, depending on what you assume for that, we were able to reach between 6 and 11%. So this shows that you can also do some early evaluation on your hardware, for example. So you can see if this is at all relevant to you, if these are speedups which are desirable, if these are speedups which are worth it for you if you want to implement this in memory computing at a very early stage without actually having to go through with it. So yeah, coming to a wrap up with the future directions. Of course, we want to do some further verification as well of our CHERI-VP implementation. Also looking at how we can add some more formal verification on top of what we've done so far with just simulating some random instructions with the TestRIG. The integration of symbolic execution, as I mentioned, to do this exploration of firmware, of software, and finally evaluate the in-memory computing model we have under different, more realistic conditions, maybe, and see how they also can be mapped to RTL then in the end. Okay, so that's it. I'm open to questions.
Is this live? Thank you very much. So, we have time for a quick question. Anybody has a quick question? Yeah.
Have you dropped this into a sort of small SOC level TLM simulation? So looked at the interact, because you mentioned that you needed to think about how you represent capabilities, I guess, on the TLM model. Mm-hmm. Have you looked at the impact on other parts of the TLM model that come out of that?
So I know that we had to do some modification to the SystemC kernel itself to handle the, of course, over the bus operations to really transport the tags and so on. But we have not done any exhaustive evaluation yet on what kind of impact that has. But that might be something worth looking into. I agree.
Thank you. Oh, sorry, Samuel.
Thank you. That was a cool talk. I had a question. So as someone not familiar with these kind of virtual models, when you say that you're looking at, you investigate things and say, oh, maybe we find ways to get speed ups. Mm-hmm. How, as someone who's very familiar with simulators and sort of like in simulators, you might be able to find things that you can find speed ups that you wouldn't be able to actually implement in hardware. Is there going to be any difficulty in translating the optimizations that you find into real hardware?
I would say that's one of the advantages of the virtual prototypes, because you would assume, so there's this idea of high-level synthesis, right, that you could go directly to the RTL. Mm-hmm. As far as I'm aware, it's not commonly used, but that is one possibility. Mm-hmm. The other possibility is that you're modeling more closer to your actual hardware in the end, so you have a bigger likelihood of being able to achieve this. For our evaluation we did so far with the IMC, with the in-memory computing, we did not actually implement it. We were just looking at theoretical speedups for now, but that would be something we will also look into in the future.
Okay, cool. Thank you. Yeah, thanks. Yeah, it's like a bit closer than a simulator.
Great. Well, thank you very much. Thanks again.